So let's start with this bunches of gas laws. This is the follow-up to that lab that we were working on last time, the properties of gases. And if you've started working your way through the data analysis and the questions at all, you realize that you've run into a couple of different gas laws. Your very first gas law was the ideal gas law, or PV equals nRT. The big important thing about this is that it let us get moles of gas. We picked it up as part of our stoichiometry unit in chem study, along with other ways to get moles. So we learned to go grams to moles, we learned to go milliliters to liters to moles using molarity, and then we learned to turn gases into moles using the ideal gas law. And that was really kind of our primary focus with the ideal gas law, was on being able to get the number of moles so we could do our stoichiometry. From the ideal gas law, we can pick up a number of other gas laws to account for changes in temperature, pressure, volume, or amount of gas. So 2 days ago when you were working with the properties of gases, you were making some changes. Like you put some gas in the syringe, and then you changed the volume inside the syringe, and you looked at how that impacted the pressure. Sometimes you made the volume smaller, sometimes you made the volume larger, which really can be managed by doing the ideal gas law once, changing the condition, doing the ideal gas law a second time, in order to calculate what your new condition is. Or you can start to use the ideal gas law to derive some other laws. And I'm going to show you where Boyle's law comes from. And you could go through the same kind of process with all the others and eventually get there. So let's say you have a gas under some initial set of conditions. And it's described by P1 V1 equals N1. R is going to be the same all the time, so I don't have to specify that that's an initial condition. T1. And so that would describe your gas under this initial set of conditions, the ideal gas law. Now, you decide to change the volume in your syringe. Maybe you push the plunger in. You've seen from that lab that when you push the plunger in, the pressure changes to a new pressure because you changed the volume to a new volume, but because the way you had the experiment set up, the amount of gas inside the syringe doesn't change because you didn't screw it off the pressure sensor and take in more gas or let any gas out. So the number of moles of gas is still the same as what it was in the beginning. The ideal gas constant is still the same because it's a constant, and that's what it means to be a constant. And you didn't heat the syringe up or cool the syringe down, so the temperature is still the same. And so what you can see is that this side and this side of the equation are identical to one another. And there's something in math that says if two things are equal to the same thing, then those two things are equal to one another. And I have no idea what the property is called, but I do know that it's a very useful property and I can use it even though I don't know what it's called. So if those are both the same, it means these two things are the same as well. And we can get a new gas law which lets us deal with changing the pressure and the volume in one step instead of having to very, very many times use the ideal gas law to get where we want to go. So we're basically going to make a list that includes the ideal gas law and everything else that you can get if you play this kind of a game with the ideal gas law. So the ideal gas law is PV equals nRT. PV equals nRT is used when nothing is changing. So everything is constant. It's just used to deal with one singular set of conditions. It does have lots of limitations on its units, however, because of the appearance of the ideal gas constant in here. That forces us to use pressure in atmospheres, volume in liters, N has to have units of moles, and temperature has to be done in Kelvin. And then we just derived Boyle's law here, which was that the pressure times the volume will remain constant no matter what you do. So if you multiply the pressure and the volume together, even if you change something, the product of the pressure and the volume is always going to stay the same. The catch for this one working is that you have to have a constant amount of gas inside your container. So it basically means keep the lid on. And you have to have a constant temperature. But if these two things are true, then you can do this. There really are no limitations on the units as long as the pressure units match one another and the volume units match one another. We lost the ideal gas constant in doing all of this work up here, and so that lifted some of the restrictions on our units. So P1 and P2 have to match. V1 and V2 have to match. But it doesn't matter what they are. The two volumes can both be in milliliters, the two pressures can both be in PSI. As long as they're both the same, you're good to go. Now, we could play with the ideal gas law to do this for a variety of other situations and land ourselves at a variety of different laws. The next law I'm going to show you is Charles' law. And it says that the pressure divided by the temperature will always be constant. And I managed to remember that this is Charles' law because when I was a kid, there was a show on TV. Oh, wait, see, I've got the wrong one. This is the volume temperature law. Because when I went back to my TV analogy, it didn't work. There we go. Charles' law is V1 over T1 equals V2 over T2. And I remember that because when I was a kid, there was a TV show called Charles in Charge, and it was on TV. And so that's how I remember that it's temperature and volume. And it was on TV, and division is an on type situation. So V1 over T1 equals V2 over T2. This assumes that you leave a constant amount of gas inside your container and that the pressure stays constant. Essentially, you need a stretchy container. Like balloons, they change in size as your other parameters change. If it gets hotter, the balloon gets bigger. If it gets colder, the balloon gets smaller. Now, here we do have to worry a little bit about the temperature scale because we have to be operating on an absolute temperature scale. One that when the temperature goes to zero, the pressure would go to zero as well. So while it's just a limitation that V1 and V2 match, T1 and T2 have to be in Kelvin. And that avoids a couple things. It avoids ever getting zero in the denominator, and it avoids having one of these be negative and one of these be positive and getting a negative volume. But even if both of the temperatures are positive, if you dump them in there in Celsius, you're not going to get the right answer. Okay. The next one, most people call Gay-Lussac's law, although your book does Amonton's law, and it is going to be the pressure-temperature relationship. P1 over T1 equals P2 over T2. This is assuming that you don't let any gas in or out of your container, and that the volume is constant. In other words, you got to have a rigid container, like a metal can or something that can't change in shape. And the requirements or the limitations are pretty similar to the limitations on Charles' law. P1 and P2 have to match. T1 and T2 have to be in Kelvin. If we take Boyle's law, Charles' law, and Amonton's law, and we combine them, we get the ever cleverly named combined gas law, which says P1 over V1 divided by T1 equals P2 V2 over T2 as long as N is constant. That simplifies things a little bit. All you need is a closed container. It doesn't matter what kind of container it is, as long as it's got the lid on, you can use the combined gas law. The awesome thing about the combined gas law is that all the rest of them are here. If the temperature is constant, the two values for temperature cancel, and you have Boyle's law. If the pressure is constant, P1 and P2 are going to cancel one another, and you have Charles' law. If the volume is constant, V1 and V2 are going to cancel one another, and you have Amonton's law. This is the one right here that's worth knowing because all the rest of them are built into that one. The parameters on this one are exactly what you'd expect them to be. P1 and P2 match. V1 and V2 match. And as always, put that temperature in Kelvin. The last one is Avogadro's law, which is a law that makes a ton of sense. If you put more gas in the container, the pressure goes up. So it's a relationship between the number of gas particles and the volume. So it's V1, or sorry, between the pressure and the number of particles. So pressure, P1 over N1 equals P2 over N2. And this is the one that accounts for why the pressure goes up when you put more particles in the container. So our constants here have to be, V has to be constant, and T has to be constant. In order for the V to be constant, this is your rigid container. Now, as you can imagine, you can make some other iterations of these. These are just the ones that are most commonly used. In order to do this, P1 and P2 have to match. N1 and N2 have to be in moles. If the two gases happen to be identical to one another, you can get away with doing this in grams because grams and moles are directly proportional to one another. But if problems get switched up and a little more complicated and it's two different gases going in, you can't work in grams. So in a lot of ways, it's actually more valuable just to get in the habit of working in moles so that you don't run into troubles. So basically, this one's going to be given to you on your test. And all the rest of these are just variations on the theme of the ideal gas law. When P and V are beside one another, we can do this. If you want to put V and T together, you got to swing the T over here. If you want to put P and T together, you got to swing the T over here. If you want to bring over the temperature, P and V are together, swing the temperature to the other side. And if you want to work with pressure and number of moles, you got to swing the number of moles to the other side. So they give you this one, full well expecting that you understand the relationships and you can generate any of the rest of them. as you make calculations, these equations up here are going to become the PE step as you do your work. The information step then becomes just kind of a data list. And I did that for you on your lab handout. I kind of set a couple of these up to show you how to do them. Okay, on the flip side of this, just a couple things to add to the ideas. Standard temperature and pressure. You will occasionally see problems that say blah, 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 blah was done at STP. That's just telling you it was 1 atmosphere and 0 degrees Celsius. I don't know who picked this set of conditions. I mean, really, how often is the lab 0 degrees Celsius? Very few things get done at 0 degrees Celsius, but somebody picked that to be STP. And it happens that at STP, 1 mole of any gas occupies a volume of 22.4 liters, and that's what they call the molar volume of gas. I don't find it to be a particularly useful number. It is an offshoot of the ideal gas law, which I guess is why I don't find it to be a particularly useful number, because you can solve for it just like you would anything else. Pressure of exactly 1 atmosphere. What's the volume? If you have 1 mole of gas, 0.08206 liter atmospheres per mole Kelvin. And 0 degrees Celsius is 273.2 Kelvin. If you solve that, you get a volume of 22.4 liters, which I guess is the reason I don't even think it's worth brain space to talk about or to remember the 22.4, because you can always have it anytime you want it. But here's a box that's got a volume of 22.4 liters. If you need just kind of a mental image of about how much space does a gas take up, 1 mole of gas at 1 atmosphere of pressure, which it usually is here in Neenah, pretty close to that, and 0 degrees Celsius. So if you took this box outside on a nice warmish winter day or a really darn cold fall day when the temperature is freezing outside, this box would hold 1 mole of gas. Inside of our classroom where the temperature is a little bit warmer, a mole of gas would need just a little bit more space. And to give myself a visual on that box, I always think of it as a box that would comfortably hold a basketball. Like, it's about the size of the boxes for the basketballs when they're sitting on the shelf in their little boxes at Scheels. That basketball box is roughly 22.4 liters, and that gets me enough to be reasonable about my answers. Now, there's one more gas law. This one could have been mine had I been born 2 centuries ago. I could have totally thought of this. Like, some of the others are really, really hard. This one I could have figured out. Here's what Dalton's law has to say. If you put more than 1 gas in the container, the pressure in the container is the sum of the pressure of all the gases that you put in the container. Okay. I definitely could have figured that out. If it's all in there, just add up all the parts and pieces. Or in other words, the total pressure is the pressure of the first gas you put in the container, plus the pressure of the second gas, plus the pressure of the third gas, and so on and so forth until you're tired of adding gases to your paper or to your container. That's Dalton's law. Dalton's law does come in one other form, which says that the pressure contributed by an individual gas is basically proportional to how many particles or what fraction of the particles it has. So what this says is if you have 3 gases in your container and each one of them is accounting for 1/3 of the particles, each one of them contributes 1/3 of the pressure. Again, I think I could have totally figured that out. So this says that the pressure for one individual gas is equal to the mole fraction times the total pressure. Okay? So if the gas is half of the particles, it's contributing half of the pressure. If it's a fourth of the particles, it's contributing a fourth of the pressure. If it's a sixth of the particles, it's contributing a sixth of the pressure. This number right here is called the mole fraction, and it's exactly what it sounds like, the fraction of the moles. It is the moles of gas 1 divided by the total moles of gas. Well,
so I guess each gas, like no matter its composition, still provides that like same amount of
yes.
like liters of space essentially.
Yeah, each gas, regardless of what its composition is, provides essentially the same contribution to the situation. Maybe that's the best way to look at it. They take up roughly the same amount of space. They exert the same amount of pressure when they bounce off the walls. That's kind of the beauty of gases, is that they're really, really simple. Their identity doesn't matter. It only matters how many particles are present. Okay, those are the rest of the gas laws that you didn't encounter in chem study. Now, there is one little subtlety that doesn't end up mattering much, and it does kind of relate to this idea of all gases are making the same contribution. That is kind of a little bit of a lie, but it's not a bad lie because it's actually true most of the time. But we do have to consider ideal gases versus real gases. The ideal gas law has always carried this little adjective at the front, ideal gas. An ideal gas is one that meets all the criteria of the kinetic molecular theory at all temperatures and pressures. It is always described by PV equals nRT. Of course, as luck would have it, you live in the real world, full of real gases. This is actually fortunate. The only reason that anything is a liquid or a solid, including you, is because the vaporized version of all of these things happen to be real gases, which allows them to condense back into liquids and freeze onward to solids. But our things that are gases at room temperature tend to show relatively ideal behavior at normal-ish conditions. And that's why we teach people the ideal gas law. It is an excellent, excellent description of behavior as long as you stay in what's kind of a reasonable range here. So in order to understand this, we have to go back to the kinetic molecular theory and look at when things might start to not be true. So let's get our little simulation back. Okay, so here's our simulation with our gases inside, and we can start looking at our kinetic molecular theory. So with our kinetic molecular theory, it says that gases are composed of molecules that are in continuous motion, traveling in straight lines and changing directions only when they collide with others or the walls of the container. Okay. That seems like something that would be true no matter what was going on. So I think we can put a check here. Always true. The gases aren't going to start to travel in a squiggly motion for no particular reason at all. Number two, the molecules composing the gas are negligibly small compared to the distances between them. Okay. So that's why every gas particle essentially takes up the same amount of space, because the particles are really little compared to the space between them. And so if the particles is really, really, really tiny, and there's like 100 times of space before you hit the next one, whether that particle is twice as big ends up being essentially irrelevant. However, if I put enough particles in here, very tiring. I can make it so that the blue space actually is a significant volume. I can also make the pressure ridiculously high here. So at some point, you simply have so many particles in there that they're packed so tightly together that if we were to consider the volume of this container, we would actually have to take into consideration that some of those spheres are taking up a significant amount of space relative to the entire container. As opposed to when things are normal, let's see if I can, here, reset. As opposed to a more normal set of conditions where you haven't got a ridiculously high pressure at all, the vast majority of a container full of gases is actually just empty space. So this one, the molecules composing the gas are negligibly small compared to the distances between them. Fails at very high pressures. Because the particles begin to occupy a significant portion of the container volume. So essentially, it becomes so crowded that we can no longer pretend that the particles aren't taking up any space. Number 3, the pressure exerted by a gas in a container results from collisions between the gas molecules and the container walls. Check. Always going to stay true. Number 4, gases exert no attractive or repulsive forces on each other or the container walls. Therefore, their collisions are elastic and don't involve a loss of energy. Sometimes gases, however, can turn into liquids. Imagine water vapor, for example, condenses onto your glass of lemonade. It got too cold and the particles began to stick together. And every gas has kind of a threshold temperature below which the particles begin to stick together. And that's why we can have things like liquid nitrogen, dry ice, which is solid carbon dioxide. If you get the particles to moving slowly enough, they can actually stick together instead of bouncing off of one another. So at low temperatures, and what defines low depends on the gas. It's like temperatures close to their boiling point. And that's the boiling point of the individual gas, not like the boiling point of water. But at low temperatures, temperatures that are getting close to the boiling point, particles stick together. Or in other words, are attracted to one another. And as they stick together, if two particles stick together, now they only count for one in the particle count because they're traveling together, they're hitting the wall together. And so the net effect is you have fewer total particles because they're sticking together in little pairs throughout the container. The whole gig about average kinetic energy, always true. So if we get extreme conditions, very high pressures, or very low temperatures, the ideal gas law begins to fail. But at just kind of standard room temperatures and things kind of close-ish to room temperature, the ideal gas law works very well, and we can ignore the identity of the gas. If you are ever to happen to need a very specific calculation on gases, there is a corrected version of the ideal gas law called the van der Waals equation. And I put it on the back of your sheet. It's not on your resource sheet because you're never ever going to have to use it in this class. But those of you going into engineering might need to eventually be familiar with the van der Waals equation. What the van der Waals equation does is it basically makes a correction for the other factors that are an issue. So in place of pressure in the ideal gas law, you use pressure plus n squared times A over V squared, which is basically accounting for the fact that the particles are beginning to attract to one another. And that little a is kind of a measure of how sticky the particles are, or what's their overall tendency to stick together. Essentially what this is that if the particles stick together due to intermolecular forces, they're traveling in pairs. And if they travel in pairs, the pressure is smaller than it's expected to be. So you have to add that little bit back onto the pressure to make this work again. The other issue is space taken up by the particles. And that's what this B value is right here. At high pressures, the particles are close enough to one another that the size of the particle becomes significant. This is essentially number of particles times the volume of an individual particle. And so the overall volume ends up needing to be corrected. If the particles are taking up space, it makes the actual volume that the gas needs to have be greater than what it's expected to be. So to make the calculation work, you have to subtract out the space taken up by the particles. Like I said, not something you're going to necessarily need for this class, but when you run across it later in life, I want you to just be aware that when they have to make very, very precise calculations about gases, they do have a way to correct for the type of gas, the amount of space it occupies, and how well it sticks together. For the purposes of this class, you need to know why the problems result. That as the pressure, or that as the temperature gets low, the pressure gets messed up because the particles are sticking together and not as many of them are available to hit the walls. And you need to know that as the pressure gets very high, that causes problems because the particles themselves start to take up some space. Okay, so that takes care of all of the things we need to take care of for that. At this point,